Problem 1.12 is very similar to the example problem on page 15. So here we are given a state function of the form this, where B is given to be 3 nanometers. And if a measurement of X is made at this time in the system, we need to find the probability that the result lies between 0.9 nanometer and 0.9001 nanometers. And the question clearly asks us to treat this interval as infinitesimal. So the interval here, dx, is 0.9001 nanometers minus 0.9 nanometers, which is 0.0001 nanometers. So that's the interval. And this is clearly this is an infinitesimal interval, so super short, small interval. And for cases like this, the probability is computed as just this. However, if the interval is not infinitesimal, then we would have to integrate over this value. But since the interval here is infinitesimal, all we have to do is compute this value. So let's do exactly that. So let's try and compute psi squared first, because we already know what dx is. It's this value. So psi squared would be 2 over b cubed times x squared times e to the negative 2. Yes. We're just squaring the value of psi. Now we can consider x to be 0.9 nanometers. And so this can be written as, if we're going to substitute the values, this will be 3 cubed times nanometer cubed. If we have an x squared, that will be 0.9 squared, squared. And we have 2 times 0.9 nanometer divided by 3 nanometers. So I'm going to do a unit cancellation there, and this 3 can do that. So this will be 2 over 27 nano, actually, it's going to be 2 over 27. And the nanometer square and the cube can get cancelled, so we have a nanometer. And here we have 0.9 squared, which is 0.81 times e to the negative 0.6. Now what we're going to do, okay, now that we have psi squared, let's compute psi squared dx, which is the probability. So let's actually go ahead and compute these values. That would be 2 times 0.81, which would be 1.62. We're going to compute e to the power negative 0.6 times this value. I'm going to divide the whole thing by 27. So I get 0.0329 nanometer inverse times dx is 0.0001 nanometers. So I am going to go ahead and cancel these two, and I will end up with the probability of 3.29 times 10 to the negative. That this is 10 to the negative 4, so 10 to the negative 6. So that will be the probability. Now moving on to part B. So in part B, we need to find the probability that system lies between 0 nanometers and 2 nanometers. So here the interval is actually 2 nanometers. This is definitely not infinitesimal. So the probability is computed as an integral of this value between 0 and 2 nanometers. So let's do this. We know from before the value of psi is given here. So let's just get psi squared, which would be 2 over b cubed times x squared times e to the negative 2x by b. So because we're working with an interval from 0 to 2, mod x would just be x, because we have positive numbers, times dx. So we're going to integrate this term. But before we do that, let's just pull out 2 over 3 cubed and on the right 27 cubed, the constant outside. And now let's integrate x squared times e to the negative 2x by b dx. So I'm not going to copy down the whole thing. Now I'm just going to focus on this integral. This integral is of the form x squared e to the power bx dx. And from the appendix of integrals, we see that this has a value of this. So it's 8.7, table 8.5 integrals in the appendix. So we get the value from there. Let's adapt this to our situation, and we can have something like this would be e to the power, in our case, b is actually negative 2 by b. So we have the exponential term as it is, and x squared by the exponential term, the b here, for us, it's going to be negative 2 over b, and I'm going to carry that b to the numerator. 2x over b squared, negative 2 over b whole squared, plus 2 over negative 2 over b whole cubed. So if we were to adapt this equation to our problem, this is what we end up with. So I'm gonna continue it here. So it's gonna be, and remember to put the limits. We need to evaluate it with respect to these limits. Times negative bx squared over 2, negative 2x b squared over 4. Now this will give 2, so I'm just gonna erase that part. Minus, because you have a cube over a negative sign, so the negative sign stays that way. And b cubed by, you have 2 over 2 cubed, that's gonna be 2 square, which is 4. So I'm just gonna write 4 in here, and we have simplified it to the maximum extent possible. So now let's just plug in the values and evaluate. That will be e to the negative 2 times 2 nanometer over 3 nanometers times the value of b is given to be 3 nanometers. So negative 3 . x squared, right? So 2 squared here would actually be 4. It's not 2, it's going to be 2 squared, which is x squared is 2 squared. So you have a 4 minus 2 nanometers times 3 squared is 9. So minus 3 cubed is 27 nanometers cubed by 4. Now from this big value, we are going to subtract. Now we have x to be 0, right? So e to the power 0 is going to be 1 multiplied by this term with x equals 0 is going to be 0 minus 27 by 4. So this is going to be, let me change the color to show how the cancellations work out. The nanometer and the nanometer gets canceled. Well, that's the only cancellation we had there. So we're going to have e to the negative 4 over 3 times negative 2 ones and 2 twos, so negative 6 nanometer cubed, negative 9 nanometer cubed, negative 27 by 4 nanometer cubed, minus, here we already have a minus, so the minus of minus is going to be plus 27 by 4 nanometer cubed. So this will be the step that we need to compute. So let's see where we started. So the probability is going to be this term times this term. So we have a 2 over 27 nanometer cubed right there. So now what I'm going to do is I'm going to write probability is going to be 2 over 27 nanometer cubed times this value. So let's evaluate this term and see what it turns out to be. I have evaluated the exponential term and it turns out to be something like this. And I basically carried out the addition here and I get this. And this term is this. And all of these have the nanometer cubed in common. So I just took it outside. Now I'm just gonna cancel that out, which makes our probability unitless, which is what it's supposed to be. So if we were to simplify this, we will have 0.074074 times 21.75 times 0.2636. It's gonna be this, right? So minus, it's a negative sign. So I will have 1.0167 approximately. So the probability is going to be 0.074074 multiplied by 1.0167. It's going to give me 0.0753. Now let's move on to part C. So in part C, for what value of X is the probability density a minimum? Okay, the probability density is given by this. And we need to find out for what value of X does the probability density become minimal. So let's first write down what the probability density is. It's 2 over b cubed times x squared times e to the negative x squared over b. So we don't really have to compute anything. As we can see, whether we have a positive integer or a negative integer, x squared is always going to be a positive value, right? It's always going to be greater than 1. So if we want to have a minimum probability that can happen when x is equal to 0, right? When x is equal to 0, this value becomes 0. So without really having to compute anything, we can just say that the probability density is minimum when x is equal to 0. So that's the answer. Now let's move on to part D. Part D is very simple. All we have to do is to verify that the wave function or the state function psi is normalized. And the condition for normalization is that when you integrate from negative infinity to infinity, the probability should be 1. All this tells us that the probability of finding the particle somewhere between negative infinity to infinity has to be 1. So the particle has to be present somewhere, right? So that's what the normalization tells us. And all we have to do is compute psi squared and then perform this integral and show that it's actually equal to 1. Now, a tricky thing here is that we have this term, modulus of x here. So the definition of a modulus of x states that modulus of x is equal to x when x is greater than 0, is equal to negative x when x is less than 0, is equal to 0 when x is equal to 0. So we cannot directly compute the integral from negative infinity to infinity. We will have to split it up such that we compute an integral for all the negative values of x. And then we compute another integral for all the positive values of x. So we'll have to compute these two integrals. And in order to do that, let's actually take a quick look at the value of psi squared. It's going to be, we've done it in the previous parts, it's going to be 2 over b cubed times x squared times e to the negative 2 times log x over b. So this is the value of psi squared. Right, now when we compute the integral from negative infinity to 0, it's going to be squared times e to the power negative 2 times the value of modulus of x when x takes negative values is minus x. So we're going to write that. Negative becomes positive. So this integral is basically going to be 2 over b cubed times x squared times e to the power 2x over b dx. Now, from the appendix of integrals, we know how to solve these integrals. We have done this in this problem. So if you have an integral of the form x squared times e to the cx dx, then the answer is going to be e to the cx times x squared over c minus 2x over c squared plus 2 over c cubed. So this is how we solve an integral of this form. And in our case, c is equal to 2 over b. So this integral can be written as b cubed can be, sorry, 2 over b cubed can be taken outside the integral, and I can write it as e to the power 2x over b times have x squared over 2 over b It's 2x over 4b squared plus 2 over 2 cubed is 8. And now I have to apply the limits, negative infinity to infinity. So 2 1s and it's going to be 2 4s. So in the upper limit, when x is equal to 0, e to the power 0 is going to be 1, right? So I'll have 1 times anything in the numerator. When you have a 0, it's going to be 0 minus 0 plus b cubed over 4. So this value is just going to be b cubed over 4. Now, when you have x as negative infinity, you're going to have e to the power negative infinity, which is nothing but e to the power negative infinity. You have a huge value in the denominator, which means this term is 0. E to the power negative infinity is actually 0. So when 0 multiplies the rest of the terms here, we're going to get a 0 anyway. So when x is negative infinity, the value of this integral is going to be 0. So the final value of the integral is going to be 2 over b cubed times b cubed over 4, which is going to be, after I cancel these terms, 1/2. Now, let's compute the same integral, however, this time from 0 to infinity. Okay. This integral will have basically the same form as what we have seen here, except that the limits will be from 0 to infinity. So it will be 2 over b cubed times x over b times bx squared 2 2x squared plus b cubed over 4, 0 to infinity. Now, when I'm sorry, you will have a negative sign because yeah. So yeah, in the value of psi squared, we have 2 over b cubed x squared e to the power negative 2 modulus of x, right? So when we look at the integral from 0 to infinity, when we look at all positive values, modulus of x is just going to be x. So you will basically end up with an exponent that is minus 2x over b. So my bad, I'm gonna add a negative 2x there. And we'll have a negative sign here. And you will have a negative sign here. Right, because you have, wherever you have c and c cubed, will be negative 2 over b and negative 2 over b cubed. So the negative sign will be present here. Now, when x is infinity, this term here will be e to the power negative infinity, and it's going to be 0. So the integral value is going to be 0 when x is infinity. That is simple. When x is equal to 0, e to the power 0 is going to be 1. 0 minus 0 minus b cubed over 4. So we're going to have negative b cubed over 4. So the total value of this integral is going to be, at infinity it's 0 minus, at 0 it's negative b cubed over 4. So the value is going to be b cubed over 4. I'm sorry, I actually forgot the 2 over b cubed part. B cubed here. Now, if we simplify this by canceling out some stuff, two ones and two twos, so this is going to be half, right? Now, the total integral from negative infinity to infinity psi squared dx is going to be the integral from negative infinity to 0, which is half what we have here, plus the integral from 0 to infinity, which is another half, which we have here. So these two sum up to 1, hence we show that psi is normalized. The state function is actually normalized. This is what we show.